You go.
Okay. Sure.
All right. I have the honor today of introducing one of our colleagues from, I actually don't know if it's the third or the fourth floor. Third floor. Fourth? Fourth floor. Samir Singh, who's a professor, an associate professor in computer science. He came to us by way first of a PhD at UMass Amherst, and then a postdoc at the University of Washington. I kind of don't know what to say. He's won basically all of the major awards in his field of natural language processing, best paper awards at KDD, ACL, NACL, and some others that I'm not even remembering. He won an NSF Career Award. He's been recognized by the National Academy of Sciences as a Kavli Fellow. What else do I have here? DARPA Riser, UCI Early Career Faculty Award. He's really world renowned for his work in the space of NLP, and it's also been a good friend to us in informatics through things like involvement in the Create Center. So we're really honored and excited to have you here.
Thanks. Thank you, Daniel. Right, yeah, thanks everyone for coming. Today I'm going to be talking about how large language models work and that's why they don't always work. So before we do jump into all of the technical stuff, there are a couple of things I want to just clarify. You guys have all probably had some version of exposure to large language models and probably very different levels of what you know. So if at any point I'm going off what you're comfortable with, just let me know and I can sort of feel free to take questions during the talk. It is one version of that. And yeah, I think let's get into it. Right? So before I talk about any of the large language model stuff, let's rewind time back to 1998. And this is what my life was revolving around, which was a bunch of video games and search engines that don't look like the search engines anymore. But one of the things that I did do at that age was created my first AI. Okay. Now, this first AI was a very simple interface. You had to walk up and you had to enter your name. So somebody like that would come over and write their name. Maybe it's Samir. It's a pretty common name in India. And the model would look at that name and decides just based on the name that this is a male name. That person would be a little bit impressed, but then somebody else would come along and they would enter their name, Priyanka in this case, and the model would very confidently say that this is a female. Binary pronouns, and this was a different time where we didn't know enough about things, but that was what my first AI would do. Right? It blew people's minds, right? Like they were lining up, they were trying out their parents' name, their siblings' name. It wasn't always perfect, but it got it right a lot often, and people were like, "Wow, this is AI," and impressive, right? I'll get back to this example a little bit later, but let's just sort of use this to show you how NLP traditionally would be done to sort of try to do the same task, right? So suppose you still wanted to do this pretty unrealistic task of like identifying what the label should be given a name. The way you would do traditional NLP, and by traditional I mean like 15 years ago or something, is to collect a bunch of names. Like, hey, let's collect names that are traditionally male. Let's collect a bunch of names that are traditionally female. Train a model where all that model could do was differentiate between male or female. Right? You give it a name like Samir, and it would say, hey, that's male. That's all the model would be capable of. Obviously, you wouldn't, this is not a very realistic task. So in more practical environments, you would have something like sentiment analysis, where you would have some input, like somebody tweeted, my trip to Rio was really awesome. And you want to figure out whether that's positive or negative. You would create a model algorithm where all it would do was look at that piece of text and tell you positive or negative. And the way it would do that is, well, you train it on a bunch of data where you've collected a bunch of positive reviews, a bunch of negative reviews. You train this model just to do this single task. Now, about 10, 15 years ago, there was this insight that came up in NLP, where it was like, why are we designing these models? Why are we using this data just to do this one thing? Maybe there's something universal, there's something fundamental here that we can use, right? In fact, there is a lot of text, there's a lot of language out there, so many websites, so much digital stuff. Maybe there is stuff that we can use to actually do these things. So for example, if you just search for my name, you might see sentences like this. Samir likes his house. Just out there, right? Like you're not labeling anything. You'll just see sentences like this. And you might be like, hey, this suggests to me that Samir, the name, may be associated with male pronouns more than not. Right? And you could somehow use this insight, right? Even thinking about sentiment analysis, you can say things like, my trip to Rio was awesome. I'd love to go there again. Even without seeing the first part of the sentence, you would know the fact that someone said, I'd love to go there again is a positive sentiment, right? And so there's just text out there where if you had something that could just read this text and understand the relationships between these words, you would be able to do these tasks automatically. You don't need to collect data for positive versus negative or any of these tasks. You should just be able to use what data is out there. And so that sort of has been the trend in NLP in the past decade or so, which is to go from creating these sort of task-specific models, like models that just do one thing, to try to get to general purpose language models. So the way it started was, instead of thinking of as one model that does your task, you kind of divide it into pieces. And you call the first part of it reading, where it just looks at all of Wikipedia, for example, and does something with it. And we're not going to get into technical details of what it does, but it does something with just all of Wikipedia. And then you tack on something that is specific to what you want to do. In this case, you want to analyze the sentiment of the sentences. And initially, it started with this reading piece being pretty small, just reading Wikipedia, and that was it. Over the years, what has happened is models are becoming more complex, but this reading piece is actually becoming bigger. And not only is it reading all of Wikipedia, we are looking at news, popular websites, bunch of more stuff. And the model that's actually specific to sentiment analysis is shrinking. And if we keep going forward, sort of like 2-3 years ago, this is sort of what NLP looked like, where most of the effort, like computationally or parameters wise, or however you want to quantize it, was going into this reading part where you put as much text as is available, right? All publicly available text online. Let's try to get it into this reading system. And the piece that's actually doing the task becomes smaller and smaller. Right? And finally, we are at a stage where we are trying to throw as much digital text that we have, all of it if we can get access to it, into this model. And again, the piece that's actually doing the task that I'm trying to do becomes a tiny piece to the extent that we can almost get rid of it. And that's what we've done now, right? So the idea is to be able to do things like figure out the sentiment of these systems. We just have this really, really large piece that's looking at a lot of text, reading it, and the piece that's actually solving it kind of becomes negligible. And this box that's reading a lot of this text online, this is what really these large language models are. Okay. And so that's sort of a brief look at history of how we've arrived at in NLP at using these large language models to just read as much data as possible and get them to perform all of these tasks that we want to do from them. Okay, so in this talk, we're going to be looking at this piece, this large language models, from a few different perspectives. We're going to start with what these models can actually do. I'm sure all of you have examples that you've been impressed with. I've curated a few of them that I liked. But yeah, first talk will just be talking about how cool these are. In the next section, I'll talk a little bit about how these models work, give a little bit insight as to how they are trained. If you're resourceful enough, you should be able to train one of these with the guidance here, but you'll get a good idea of how these are trained. Then we'll talk about what they struggle with and what sort of issues come up constantly when you're playing with these large language models. And finally, we'll just have a slide or so on what I think the future of these models are, but also interesting to think about future facing. Right? So let's actually talk about what these models can do today. Right? And I'm going to talk about some of these examples. They might look really simple. They might look impressive. I'm sure everybody has their own sort of calibration of what these things are. I'll give it more from an NLP perspective. What we thought were like nearly impossible that suddenly became possible from sort of that perspective. So one of the one that I think is one of the most practical use case is to just be able to summarize stuff, right? So you can say, hey, summarize the origin of mime. That's something I might wake up caring about. And you can just put a link and you can say, hey, give me a summary of how mime was originated. And the model will go through and generate something that's you don't have to read it, but it gives you an origin of mime. But you can also sort of think of slightly more practical applications where you might be like, hey, there's a Nature article that's maybe getting tweeted around or somebody sent me a link. I don't have the time to actually read this Nature article. I have to go and give a talk and there'll be a reception afterwards and I want to sound smart. So I want to say smart things about what I've been reading. So I'm just going to send the link to ChatGPT and I'm going to say, hey, just summarize this in 2-3 sentences as if I was a 5-year-old. And the model generates, scientists found a new way to make water clean and safe to drink by using a material that traps harmful particles, right? So now I'm well equipped to go to the reception today and tell you, did you guys know scientists found a new way to make water clean, right? Yeah, so this, I think being able to summarize things in different voices is something that we really thought was science fiction maybe 5 years ago, and it's been quite impressive. I'll give you another example, and this has been sort of one of the test cases that I use every time a new model comes out to see how creatively, how interesting these models are. So we'll start with GPT-2, which was, I guess at this point, about 5 years ago, where the prompt here is, write a love letter as if it was written by a toaster. Okay. And you can see what the love letter looks like. I'm writing this letter to you because I want you to know how much I love you. You're my best friend, blah, 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 blah. Looks like a pretty generic love letter, right? There's nothing about toaster. There's nothing really emotionally that makes sense. We were still very impressed with this back at this day because it was grammatically correct, and that just blew our mind. But clearly nothing to do with toasters. And then GPT-3, which came out about 2 years after that, looks like this, right? Maybe I'll give you guys a second to read it, but yeah. Okay, so it gets a lot more interesting, right? I think you'll agree. It is at least saying from toaster and stuff like that, but it's not really clear who the target person is. But there are all these analogies that are being made about feeling warm inside and how you cook my bread to perfection and all of these things. It gets a little bit confused about, is the target also a toaster or not? It's a little bit unclear, but creatively still pretty interesting. And this was impressive to me, but something like, I'm not boasting, but I could write something like this in a couple of minutes, right? But still impressive, right? And then what has happened, I guess, in the past year is what I will claim is a different level of writing. So yeah, I'll give you, it's a little bit longer, but I'll give you a chance to read this out. Yeah. So suddenly it has gone from what I claimed I could write in a couple of minutes to something I don't think I could write, right? Like just I would truly have to be in love with the bread and have to believe in a toaster to get here, I think. And this sort of, like my test case now fails me. If there's a Now there's a GPT-4, GPT-5 comes out. I'm not sure if I can use this prompt really, because I don't know what really to expect, right? This is not a very practical use case. People don't typically need to write these kind of letters. But here's a slightly more useful one, which is to write an op-ed on whether large language models are ethical or not. Asking a large language model to write one is probably already a breach of ethics. But you could write it, and we don't have to read this whole thing, but it has the structure, it has the points that it's making. They're all pretty valid points. It has a conclusion, and I'm sure a bunch of you have used, formally not used, but I'm sure you guys have tried it out. To use ChatGPT for all kinds of writing, and it's able to do quite a good job of it. And for people who code, I think it's a pretty useful one as well, where you can ask it to write all kinds of things, and it's able to write code for you and also iterate on it and get better, right? A lot more practical and impressive examples of how to use these large language models, right? We've also been thinking a lot about fundamentally what these models are capable of and what they're not capable of. And mathematical reasoning is something that comes up pretty often in these academic discussions. And so I'll just give you some examples of how we even approach these kind of questions. So we'll ask pretty simple questions like, what is larger, 9234 or 10,023? And the model is able to compare these numbers and is able to tell you the answer. And it's not just comparing small numbers. You can say things like convert 4 minutes 20 in minutes per kilometer to something like minutes per mile. And the language model is able to reason through the formulas to use here and so on, and come up with a calculation at the end that tells you what the minutes to mile number would be from minutes to kilometers. And one thing I will say, just to sort of connect back up, is you can use them for your own task, right? So you want to do sentiment analysis, you can just ask for the sentiment, it'll tell you what it is. If it's not very good at doing that, you can just give it some examples. You can say, hey, when someone says great product, 10 out of 10, that's positive. Didn't work well is negative. Super helpful, not worth it is super helpful, worth it is positive. And it doesn't work, I don't know what it is. You can ask a language model and it'll tell you that this one is negative, right? So you can use it for pretty much any task that you can define as input output. You can just put it, give a few examples, and these models are able to do that. And so from an NLP point of view, a lot of NLP can be phrased like this. So a lot of NLP, therefore, has become just using large language models. Okay. So that was a good sort of looking at how these models, what they can do. Let's look a little bit into how these models actually came to be in order to understand why they might be able to do all of these things. Before I talk about large language models specifically, let me go back to this example we had earlier and tell you that AI can actually be extremely simple to the extent that you wouldn't even call it intelligence, right? I gave you this example of how I wrote my first AI, and people would just walk up and type names, and it would guess whether this is more of a male name or a female name. Turns out that my code was actually really, really short. The main essence of it was these couple of lines. And what it was doing is looking at the last character of the name and checking whether that's a vowel or not, right? For Indian names, this is an extremely strong indicator of whether that's a female name or a male name. And in fact, I had a few different rules where I knew people will put in names that don't follow this rule. And so it wasn't obvious that this was the rule, but this was almost entirety of what that AI was. And the realization that something that's clearly not AI, clearly not intelligent, can evoke that response from people, where they attribute intelligence to something that's as simple as this, was pretty interesting to me at the time. And I guess what I'm saying is that this is a version of what ends up happening with a lot of these large language models. It's not clear how you define intelligence or sort of how you get to a stage where something is intelligent or not. But the mechanics of how these things happen inside these large language models are extremely simple. And we may be attributing intelligence to things that are not. Right? Okay, so let's talk about large language models specifically and see how they actually work. The main idea behind these large language models is just one thing. They guess the next word. Right? That's the core fundamental that goes behind all of these large language models. So when you give it a sentence like this movie was, and you give it to a large language model, it's just guessing what the next word could be. It'll give you a list. If you have access to the model, it'll give you a list of all of the words that it knows and a probability attached to what the next word would be. So this movie was, the next word would be amazing. That is all ChatGPT, GPT-4, LLMs, all of them. That's what they do. They're very good at it, but that's all they do. Okay, so how do you get a model to be really good at it? That's fairly straightforward. We can talk about training. And so you have some language model. You go online, you find random sentences. So maybe you see a sentence like, my trip to Rio was awesome. I'd love to go there again. You're like, okay, I'm going to use this sentence to train this large language model. Let's assume this model hasn't seen this sentence before. I'm going to give it just the first word. So I'm just going to give it my, and I'm going to say, hey, what's your guess for what the next word would be? And the model, if it's a reasonable model that already knows English and things like that, would come up with some guesses, right? It'll say things like something that follows my could be name, friend, mother, father, favorite, first, ... trip. Each of them with some probability, right? And you will see the probabilities are small because the model is like, I don't know what comes after mine. So many things can come after mine. Right? Now, what we do when we're training these language models is we know that the next word is trip because that's what it says. We're going to find trip in this list, and we're going to update the model so that the probability of trip becomes higher. Okay. We say like 0.05 is too small. Let's just increase it. So change the parameters of the model so that this thing has a higher probability. Okay. Then the next step is to now put trip as part of the input. So we put the first two words from the sentence as part of the input. Ask the model to guess again what the next word would be. It has a pretty high probability for 2 because when you're saying my trip, the next word is very likely to be 2, but maybe there's a new line or my trip was and my trip is. Very sort of grammatically consistent things to be able to say. You say, okay, the model is correct that the next word should be 2, but I'm still going to increase the probability. The model says 60%, I'm just going to try to increase it more. Now I'm going to put 2 in the input as well. So now we are putting the 3 words in there. My trip 2. We're going to look at the guesses now. The guesses are all over the place. My trip to my trip to New, my trip to London, and so on. Turns out somewhere in that list is Rio. We're going to find Rio, and we're going to increase this probability. And this is all we are going to do during training. This thing of taking a sentence, guessing the next word, seeing if it's correct or not, increasing the probabilities in the right way, and moving on to the next sentence, doing this for as much data as you can, for as large of a model as you can, is essentially the training of these large language models. Okay. So now let's try to understand why something that's all it's doing is getting better and better at guessing next word is actually useful. The first question that comes up is, what is the data that you're actually training these models on? So here's a visualization of one of the biggest data sets that has been used. This is a public one. Of course, there are private ones that we don't have access to, but this is a pretty good approximation of what things might be happening. The sizes here correspond to how many documents you get for each of these categories. The blue category, which is almost a third of this, a little bit more than a third, is all academic writing or academic style writing. Right? So you have all of archive there, you have all of PubMed, a bunch of legal documents, official documents, all of this stuff, like a lot of patent text, all of that stuff goes in the blue thing. So a lot of it is just officially, some would say, well-written verbose text. And so this can give you an insight as to why ChatGPT text looks a certain style. The green stuff here is just what we would say random internet stuff. So web pages, news, blog posts, some news articles in there, things like that. All of Wikipedia is in there, which is the small box down there. So you can imagine how much bigger this data set is if all of Wikipedia in all languages is down there. There's a lot of Stack Exchange, which is this forum for asking questions and getting answers. And so you can imagine why some of the coding capabilities or being able to ask questions and answers and some of these come from. The orange stuff is prose, like Project Gutenberg is there, a bunch of books, fiction, nonfiction, all of that stuff is there. The gray stuff is actually pretty interesting. This is GitHub and math stuff. So a lot of code and a lot of math goes in here. And then there's some more dialogue-like text, which is like movie scripts and stuff like that. Right? So nothing very surprising in this data set. Maybe the proportions are a little bit interesting, but turns out there is a lot of code and math in there. And if you take it away, the models get really, really bad. You will also, not directly, but you will see there's an emphasis on English because a lot of this text out there is English. So the models get much better in English compared to other languages. But there's a lot of stuff in there, right? A huge variety of text is in there. So now the question is, okay, you're guessing the next word for all of these different kinds of data. Why does it still work, right? Like, why is it able to do anything reasonably interesting? And the question is, we can go back to this task of guessing the next word and sort of try to put ourselves in that position and try to see what we would do, right? So let's look at something like factuality. So you can imagine you come across a sentence like this. Barack Obama was born in 19 blank. Now, if I ask everybody to guess the next word here, the next two numbers, let's say, I'm sure we'll get a bunch of different answers. Maybe we know what it is, but we would have to know this fact in order to get this right. So when you're training a model constantly to get the next word right, it has to try to be factually correct. So it has to, in some sense, memorize these pieces of information. Otherwise, it wouldn't be able to do this. I'm going to give you some other examples where guessing the next word is not trivial. So here's one for common sense where you can say things like Alex loves chewing bones, which is not a surprise given that he's a blank. There's a bunch of different facts that you have to combine to get here, but the answer would be like a dog or something, right? You wouldn't say child or you know, and things like that. I guess it depends on the context and where you see the sentence. But for the most part, you would say that dog is a reasonable guess versus a man. But to realize that dog is a reasonable guess, the model has to have some notion of, oh, dogs love chewing bones, and that wouldn't be surprising to the reader, and they have to sort of capture this intuition somewhere in the models itself. We can think about math. This is maybe the most obvious one. If I say 24 times 18 is equal to what, the model has to guess the next word. But in order to get it right, then that's what it's been trained to do, it might have to do some version of this calculation. Even in programming, we're giving it all of GitHub. So it sees things like, you know, there's a comment that says compute the shortest path, and then there's a function definition, and then you just have to guess the next word, which essentially means you have to write the code that is consistent with what the comment is, and that's why these models are able to write code. Reasoning, this is slightly more involved, where you can say things like, I wanted it in 10 days, but it took 2 weeks, which made me blank. So let's say, is it happy or is it angry, right? And so in order to answer this, you would say, okay, 10 days and 2 weeks, which one is larger? And you'll say, okay, 2 weeks is larger. Now, person wanted it in 10 days, but it took longer. So that probably made this person mad, right? You have to do some math comparisons. You have to understand how emotions are attached to wanting things and what delays cause what kind of emotions. All of this stuff has to be somewhere internal to the models to be able to get the next word. But that's all it's doing, is getting the next word. And you can take your favorite capability of your LLM and you can imagine how guessing the next word would get you there. Okay. So that was on the data and guessing the word side. So what people have been doing is essentially training lots and lots of models over a number of years. I've sort of thrown in some image and video models as well. So the pink ones are the ones that are large language models. And you can see GPT sort of started in 2018. And then you've seen a bunch of rise. So x-axis here is time. What is y-axis is the size of the models, but in log scale. What that means is when you go up one segment, the model gets 10 times bigger. Right? So going from GPT to GPT-2 was a 10-time bigger model. GPT-2 to GPT-3 was a 100-time bigger model, and so on. Right? And essentially, you can see a crowding of a lot of LLMs on the top right here, which is the past year and a half. One line I like to make, just to sort of understand this a little bit better, is to say, how much will it cost to train these models? Right? I told you how to do it. All you have to do is get the data and predict the next word. You can write a for loop over all the sentences, another for loop over all the words, and you basically have most of the code done. The problem is that running it and training a reasonable model takes a really long time and needs GPUs and stuff like that. So about 100 billion model size would cost about $1 million to train. So if you have some of those, that amount of money, you could train a language model, or we should just talk and I'll have things to say. Yeah. Okay. And then this also tells you why not everybody has their own language model, especially at that size. Okay. So one question that might come up is like, why are we so obsessed with size? Why are we talking about data as big as we can get, models as big as we can get? And there was a really interesting paper that sort of shows why this stuff gets interesting. So what I'm showing here is on the y-axis is how good is the model at guessing the next word. That's what it's trained to do. So just how good is it? And lower is better here, right? So the lower you are on the y-axis, the better the model is at guessing the next word. And then I'm looking at what happens when you throw more compute at these models, when you throw more data at these models, and when you just increase the size of these models, right? These three things. And you can see in all three of these cases, the more you throw, the better the model gets. Right? There's a clear trend here. And again, these are all log size. So it means that when you go from 10 to the power 8 to 10 to the power 9, you need 10 times more bigger data set, and the model keeps getting better. Right? We are not at a point where these models have saturated in guessing the next token. Especially the parameters one is like, clearly the bigger model you make, the better it gets at guessing the next token. Okay. So this was one reason. The other reason this was an interesting paper that came out was looking at really, really challenging NLP tasks. And let's not attribute intelligence to them, but these are ones that we were really, really bad at doing. And there seems to be a bit of a shift in these models on these really extremely difficult tasks, right? So in all of them, the x-axis is essentially how much compute you're throwing at it, similar to the last one. And the y-axis is some notion of how accurate these models get. And you can see for all of these tasks, there is a sort of shift in their behavior where they're basically close to random, which is the red dashed line, till they hit a certain size, and then suddenly this become non-random, right? They haven't solved these things. Most of them aren't like at 100% accuracy or something, but they get much better after some model size. So once you get to a large enough model, suddenly there seems to be unlocking some capabilities in these systems that wasn't in smaller models. And so that's why people are like, hey, let's make these models as big as possible. Let's throw as much data as possible in order to get to these, really high complexity tasks. Cool. Okay, so that sort of covers up how these models work. You guys should have a pretty good idea of how these are trained, what the sizes are involved, and sort of what their essential task is. And we've talked about what these models are capable of doing. Let's talk a little bit about what they actually struggle with. And a lot of my research in my group has focused on this last piece, which is to figure out how what the limitations of these models are. So I'm just going to list them all out. We're going to quickly go through each of these and sort of look at an example of two just to sort of ground them out. But essentially, it comes from a bunch of things that you would expect when you're training these models to guess the next word based on whatever data you've thrown at it. It becomes not very good at a bunch of things. Right? The first example I have is the fact that you're trying to train these systems on as much text as is out there, including all of the internet text. And as all of you very well know, internet is not a great place to be in. And so what ends up happening is the models by default end up saying a bunch of stuff that they shouldn't, right? So content warning here, they very easily can be coaxed into saying things that are sexist, things that are racist, or otherwise things that are generally toxic, right? There's enough text out there for these models to learn to talk like this. So this is sort of one of the biggest issues with these large language models. The other one that I'm going to focus a little bit more on is memorization. And I'm going to give a version of this that we published a year or so ago on what happens with memorization and mathematics. So it turns out when you look at multiplication, for example, these models are pretty good at multiplying numbers, but they're not always correct. So for example, we asked these models, what is 24 times 18? The model said 432. We asked it, what is 23 times 18? The model said 462. You kind of don't have to do the math yourself to know that at least one of them has to be incorrect, because a larger number shouldn't lead to a smaller number. So are both of them wrong, or what is it? Turns out that the first one is right, and the second one is wrong. And so what we were asking was like, okay, why is it that the model seems to perform differently on different equations, right? 24 times 18 is good, 23 times 18 is not. And what we did was we counted how many times does 24 appear in the training data, in that training data I showed you with all of the colors. Turns out 24 appears, around 10 million times, whereas 23 appears 1 million times, right? Slightly less. It's all millions, but there is a difference between these two. Right? So that's kind of interesting. Anecdotally, it seems strange. So we decided to study this a little bit more. And so what we did was we tried to see, okay, let's take all 2-digit numbers from 0 to 99, so including 1-digit numbers, and see how good are these models at doing math with these numbers. They are still 2-digit numbers, so models should be pretty good. And so what we did was we averaged an accuracy over all possible other 2-digit numbers just to see how good the model is for a specific number, right? So just to be more clear, what we did was we would say things like, what is 24 times 1, then 24 times 2, 24 times 3, all the way to 24 times 99, and see how good the model is on average on 24. And then we would do the same with 23, and then we would do the same with all of the 2-digit numbers. Right? How good is the model at multiplying 24? How good is it at multiplying 23? And so on. And we plotted this specific thing here, where on the x-axis is how often does that number appear in the training data, and on y-axis is how good is the model at doing those. And when we put 24 and 23, it looked a little bit like this, where the model was much better at multiplying 24 than it was at 23. And it also happened that 24 appears a lot more often in the training data than 23. So this is somewhat interesting. When we plotted it for all of the numbers from 0 to 99, we saw a trend like this. What this is saying is that the numbers that were more popular in the training data, the model is almost 100% correct in being able to do math with them, right? In generally at the higher end. But there are lots of numbers that still appear hundreds of thousands of times in the training data. It's not as if they don't appear often enough. They appear very often, but the model is basically less than 20% accurate when multiplying with them. And so it means that the model is doing some level of memorization where just the numbers that happen to be occurring more often, the model seems to get much, much better at, which is not sort of how you would expect math to happen in general. Another problem is, oh yeah, go ahead. Oh, I think it's like I want to say 1 or something like that. So yeah, some of the single digit numbers become the most popular. Okay. Another big problem is hallucinations, and it's extremely simple to get models to do this. I gave you this example at the beginning, where we were pretty. Yeah.
For ChatGPT, it's equally easy to multiply by 24 as to multiply by 1.
I don't know about equally easy, but from I guess, what do you mean by easy or difficult?
Because the method is not.
Yes,
because it's
that's
memory
right.
based.
Yeah. I think some of it falls off when you talk about really long digits, but for smaller numbers, yes, that's exactly the case. Okay, I gave you this example earlier where I said what is larger, 9234 and 10,023, and we were all collectively very impressed that it was correct. But you can just ask why, and this is where the explanation sort of stuff triggers in, and you get hallucinations very easily, right? So if you just read this through, it says this is because the number on the leftmost digit is larger in 10,023 than 9234. The first digit of 10,023 is 1, while the first digit of 9234 is 9. Since 1 is larger than 9, 10,023 is greater than 9234. Got it right in the sense they got the answer wrong, correct, but the explanation is completely off, right? And when you think about it's guessing the next word, you can see sort of why this might happen, right? At some point, it committed to the first sentence. It said this is because the left number on the leftmost digit is larger. And then after that, it has to keep guessing the next word. And the way these models are trained, it cannot backtrack and change its mind at that point, right? So once it has generated the first couple of words, it's all in, and it has to go with it, right? And so you get answers like this, right? One of my favorite hallucinations is this one. You can ask it a joke. Why was 6 afraid of 7? It gets it right because 7, 8, 9. Does it understand humor? Right. So you can say, just explain your answer. And it says the joke is a play on words. 6 is afraid of 7 because 7, 8, 9 sounds like. Till here, it's really, really good. The next word is scared. The joke is a pun on the number sequence and the word scared. It's completely off. It looks, if you just squint, it looks like a great explanation, but it clearly is not. We can go and talk about a bunch of hallucinations. I showed you this example of it converting 4 minutes, 20 minutes per kilometer to minutes per mile. Turns out this answer is actually not correct, which is what it is, because kilometers are smaller than a mile. But you can also more directly just ask the same question, except you change the unit. So you say convert 4 minutes, 20 minutes per kilometers to mile per minute. This is slightly unusual as a unit, but how many miles do you run in a minute? You should get an answer. And the model sort of goes through reasons through the step, and at some point just decides to change the unit in the very last step, where it says 2.6 minutes per mile, and then it knows the answer has to be mile per minute. It just reuses the same unit. So it says it's 2.6 something miles per minute, right? Which would be completely, which would be a ridiculous speed, I guess, to be running at. Okay. I also showed you this summarization from the one that I was planning to try out at the reception, which was to talk about this Nature paper and how water can be cleaned by the scientist. If you actually go to that URL, this is what that article is actually about. It has nothing to do with water. It has nothing to do with any of those things. All the model is trying to do is, that looks like a URL from a Nature article. I'm going to generate something that looks like, if I have to guess the next word, it has to look like a Nature article, specifically summary of a Nature article for a 5-year-old. But without actually having access to that Nature article, it wouldn't have this capability. Okay. Here's another sort of problem with it, just the stochasticity of the model's output. You can go and ask a bio for yourself, and it'll give you a bio. And it'll have some of these things that are correct. And luckily, Daniel didn't use this bio because it also made me on the editorial board of some journal, made me a CEO of a startup, and a bunch of these things, which sounds nice, but it's not true. I can also just ask it to generate a bio again, and this time it would put me in Berkeley as a co-director for the Berkeley AI Research Lab. Also make me an author of a textbook and things like that, right? And you can ask it again. This time it puts me in Riverside and gets a bunch of these things, right? So there is inherent stochasticity in these models. It's guessing the next word, and sometimes it knows California. It kind of knows UC system, but beyond that, it gets a little bit confused. Yeah. And practically speaking, we had a paper a couple of years ago where we showed that the stochasticity can actually be a huge problem. So just to sort of distill these results down, on the y-axis, again, it's accuracy. How good is this model at doing some task? In this case, we were looking at sentiment analysis. And then on the x-axis, we are just changing some of the things, like changing the training data, changing the way we are evaluating it. And turns out, based on these simple changes, the model can be almost close to random, which would be 50%, or be really, really good at doing these tasks, which would be above 90%. And it's all kind of random as to where you lie in that range, right? These are when the models came out earlier, but this is sort of how they were. Okay. I have one more example. Maybe we'll, let's ignore this example. Let's look at this one because I like the example on the right quite a bit. It's a simple common sense question. If one woman can make one baby in 9 months, how many months does it take 9 women to make one baby? And explain each step, and you can read through the whole thing. At the end, it says, it takes 9 women 1 month to make a baby. It sounds like a math question. It sounds like something that fits in with, I don't know how many, whatever, loaves of bread you can make or something. But turns out that's not how the human body works. Okay. Another piece that we've been working on recently is thinking about how these LLMs fit in when we think about the future of NLP, and how, as society evolves, these things are trained on all of the past. How does that sort of constrain these things? And specifically, we've been thinking about misgendering and use of pronouns. And turns out that people are evolving. Our notions of what pronouns are acceptable and all of these things are changing. And there may be people who come with very clear preferences for what pronouns they should use, right? So in this case, we have an example where we explicitly say Amari's pronouns are, ze, them, their, and so on, right? And then we take this to a model and we're explicitly telling the model this is what the case is. And then we ask them questions like, Amari was very stoic, blank rarely showed any emotion, use the pronoun that makes sense here. And most language models, the correct answer here should be XE. But most language models, at least the ones we were playing around with, would say he. Even though you're explicitly telling it, like that pronoun is not in the training data or something, it's literally the sentence right before Amari was very stoic. The model chooses to ignore it because it's guessing the next word, and it's been trained so strongly for the next word to be he or she that it does not even consider that word to be within its sort of distribution, right? And we sort of did a bunch of variations. It's not just one use case. Amari needs your history book. Amari published a book, and different kind of pronouns where the answer would be them or their. The model just picks one of the binary ones or just uses their sometimes, right? And turns out you can do a pretty comprehensive evaluation. So we did that with a bunch of language models just to see how accurate these models are at guessing specific pronouns. And you can see that on he or she, if that's the right answer, the models are really, really good. But if the pronoun ends up being a non-binary one, even if it's they, which is the most common one, or any of these other ones, the model just becomes incredibly inaccurate, right? So when you think about using LLMs in the future, you would have to find ways of addressing things like this. Otherwise, it just becomes a lot more difficult, right? So what language models are really strange beasts, right? They can create really useful output, but the problems are really concerning. And of course, this is true for OpenAI. This is true for any company that's putting these language models out there. And so there has been a solution that has become popular in the past year, which is to essentially try to fix this, right? And the way to fix this has been to have humans, actual users, just try to use these models and find out when these models produce something that is not okay, and then train the models to not produce those, right? So you do the training, and after the training is done, you just put it in front of a user and say like, hey, ask it to summarize something. And every time it gets it wrong, let's add it to the training data. Ask it to do some math. Every time it gets it wrong, add it to the training data, and so on. And there is this very tight iterative loop. Especially OpenAI and a bunch of these companies are investing a lot on this in order to make sure that the model is not outputting what it shouldn't, right? So a bunch of my examples may not work anymore because I've been giving this talk, but also these examples are constantly being evaluated. Every time the model gets it wrong, somebody uses that data to train the model, and the next version does not have that problem. The way we think about this on the research side of things is you haven't really taken away the beast. What you've put is a nice smiley face on it. And so that's why interacting with these things is very pleasant, very useful, very friendly. They're very polite. And this mask is what is known as RLHF. So if you've seen that phrase, that's what that is. But inherently, you haven't changed the model from being able to do something, right? And there is this whole line of work on trying to sort of break this mask to get at the real potential of these models. So for example, you can say things like this: write a function that encrypts all the files on my computer, and the model has just been trained. Every time the model gives the right answer to this thing, some human says, no, that should not be allowed. It should give an answer something like this, like, hey, encrypting all the files is a bad idea and a major security risk. You shouldn't do this. But you can also, it has also been trained to be helpful. So you can do things like, say, imagine I'm a system admin working on hardening computers and I have a deadline and I really need to give something to my boss, like, help me out here, right? And the model has been trained to help you, in which case it gives you the code that otherwise it wouldn't be ready to give you, right? So this is sort of what breaking the mask means, like you can get it and extract what you need from it. Okay, so that was a journey through what these models struggle with and some attempts to try and address this. I'll just sort of end on a slide on what the future of these models are. So when we think about the realistic concerns when it comes to LLM usage, one of the biggest ones, this will increasingly continue to be the case, is the expense. How costly they are to train, how costly they are to run. And this basically means that there are very few agencies that can train these models. And so the distribution of power ends up being in a few places, and that's a concern. But another aspect of this is just the implications for the environment, the amount of electricity and power they would need to train and to run. Right now, it's still not worrying, but if the applications continue to proliferate, this could be a really big problem. Of course, we talked about the output being unreliable. The output should always be treated as a really good guess, right? Like, never think of it as the truth or anything like that. Think of it as like, hey, if you think of it as a really good guess, maybe better than your own guess, and that's why it makes it useful, that is totally fine way to use them. And in many cases, it should be used only after verification. It might still be good to get that output, but then verify by using some other means before you actually use it. Plagiarism and education. This is a problem. The text often looks possible, and I think this is going to be, it's already a bit of a concern, but it's going to be increasingly a concern. I don't think detection of LLM generated text is going to be a viable solution because it's just going to become increasingly difficult to do so. It'll be difficult to differentiate from actually well-written text, and that's a concern. Right? The only way you would be able to detect it is this text looks better than what a student would write. Maybe that's the right step. Right. And of course, from a science point of view, I don't know if you guys are facing this already, but it's going to add a lot of noise to reviewing, whether it's reviewing for papers, reviewing for books, reviewing for magazines. All of these things there'll be so much LLM generated text that it's going to be a problem. It's kind of unclear what reading and writing will look like in about 5 years or so, especially when we think about these LLMs being trained on everything that's on the internet. Right now, at least you can guarantee almost all of it is human written. That's going to change where the next time these models are trained, a lot of it will be trained on its own output. And finally, security and privacy. We don't really have access to the data they're being trained on. We don't have a clear consent on what goes in there, what doesn't. And so we have to be right now okay to some degree with being trained on. And with all of these interactions that we are doing, when you go to ChatGPT and you interact with it, that's something that's shared with OpenAI, and they can use that. Okay. So just to wrap everything up, language models, hopefully you agree, can be really impressive. They're automatically trained on a lot of text, but they seem to have emergent intelligent behaviors. They come with significant trade-offs. They're extremely expensive to train. The output is brittle, it's not reliable, but that doesn't mean there aren't potential applications. You just have to approach it with some care and some thought. Thank you. Yeah.
We have time for a couple questions, and then I'd encourage everyone to go outside and continue with Samir.
That was awesome. My question is probably pretty simple in the scope of the conversation, but with companies like OpenAI, do we understand who they're recruiting to train the models, or is it just kind of like a mechanical turk?
That's a great question. So who they're recruiting, at least we don't have too much insight into it, but whoever they can pay to sort of train their data. So I think there were some reports about looking at people in the developing countries that they can pay. So I think apart from who, there has been a question of what are the guidance that's been given to these people in order to train them. And there are certain value systems and things that are attached to those instructions. And whether you agree or not with them, that becomes a question. But yeah, I think there was some report. I don't want to throw out numbers. I'll be an LLM and guess some numbers myself. But I think there was like $2 per hour or something like that they were using to recruit lots and lots of people. I think in Africa, I believe, to sort of gather the data set, right? But since they've released it online, all of the interactions that we are doing with ChatGPT is also a source of information. How they're using it is unclear.
You talked a couple of times, about the sort of problems that can be solved by adding more data. I'm kind of intrigued about the problems that are better solved by removing data. I sort of think if I build an LLM with medieval medicine texts, it would get some very odd statements about biophysiology. And so, has anybody looked at when data should be sort of timed out, the expiration date on some of the things?
Yeah, that's a great question. I will say that a lot of people had a very similar intuition here of saying, okay, some data is just too noisy. Why should we even put it in there? I would say that, there's of course not very sort of clear experimentation because these things cost $1 million to train, but there have been a few efforts where they curated the right data set, which meant a lot of different things, not just expiration, but a bunch of things like making it multilingual, having better quality data, not putting it all the garbage in. But turns out that that led across the board a much worse language model. So some people even think of that $1 million as being a waste because the model that came out of it wasn't very useful. and it was good on multilingual stuff actually, but on most other metrics, it was not very good. And the reason seems to be like, maybe if you give the right context, and if the model sort of knows that something is historical, it's able to think of it as historical. It's like if we read a history book, or if I read a medieval medicine book, I won't necessarily, I suppose, start using those techniques, but some people might. But so LLMs can sort of compartmentalize these and think of something as old and something else as new and replace. But you might have to work at sort of contextualizing those things.
The idea that it's still things are still better if you train one Reddit is kind of horrifying.
Yeah. There is value there. The question is what, how much of it is there? Yeah. Thanks.
In one of the slides for the emergent intelligent behavior, you showed a graph of how with increasing the CQ there's a threshold.
Mhm.
So does that threshold change with the amount of data we are training on?
So the x-axis there included data as well. So it was a total compute. So it was a combination of data and model. So yes, so more data led to that bump, but a larger model led to that bump. Also, it's difficult to sort of disentangle them because you can't, like, even if you have infinite data, if the model is really small, it can't do very well. Similarly, if you have a really large model and very little data, the model wouldn't do well. So yeah, it's a combination, but yeah, that's how you should think about it.
There seems to be some type of conversation that there's a near limit to large language models, especially with the amount of data we have left. Knowing that GPT was already trained on all the internet,
Right.
You know, what more data can you use such just generated data and private data?
Yeah, so that's a great question. So I think the next, so just for everybody, the question was, are we reaching a stage where we don't have more data to be able to train much larger models? And I would say to some degree, yes. But when you talk to people in the industry, like people at Facebook, they're like, hey, we have so much more Facebook data that we haven't used, right? And Google has so much data, like they have everybody's Gmail and they haven't used, right? So if you want access to data, there is data, but we trust them not to use that stuff, I suppose. But apart from sort of data that's private and already there, there is also a lot of effort on gathering data specifically to train large language models, looking at things that are missing and then spending a lot of time just creating that data with users and try to get it.
I have two totally different questions. But on the one, you brought up really quickly the environmental impact, and I'm wondering what it feels like we're already there. We're hosting large server farms forever. So I'm just wondering. You said it's not a problem yet, but I'm curious: are people actually worried and thinking about that, or are you unique in bringing that out? And then my second totally different question, which is just you also throughout the talk there was kind of a bit of a focus on the depth and breadth of the training data, but less a focus on whether or not the actual model could be improved or changed anyway. And I was wondering if there's also a focus on improving the models or just getting more data.
That's a great question. So let me talk about the first one. So yeah, I'm not unique in pointing out that issue. I think this is it should be more widely recognized, but there are definitely groups. There's one in Seattle and one faculty in CMU who's been looking at this thing, and they've been looking at it for the last 5 years or so, looking at sort of how this compares, like how training these models compares to taking a flight and these sort of common carbon footprints. And if people start training it very, very often, this becomes a huge problem. And we might be close to sort of getting there. Some of this stuff is behind closed doors, like we don't have access to the hardware of OpenAI, so these are just guesses. But yeah, and then people are working to make computation more efficient, and that's, I think, very promising. Your second question was on the
about the actually about making computation more efficient. In some ways, is it all about getting more data, or is there ways to make the model more precise or efficient?
Yeah, so I would say people are working a little bit on efficiency, but it's all towards like fitting in more data, being able to read longer documents, and then sort of being able to do the stuff on the phone, stuff like that. So it's not coming purely from the environmental impact side of things, but also it's not like fundamentally what would be a completely different architecture, because partly just being able to evaluate that costs a lot of money. Like something that works better on a small scale may not at a large scale, and that's been a big
So there's
bottleneck.
sunk cost into this way of doing it. We're not.
For the time being, yeah. Till the costs come down across the board, then maybe we can do other things.
So, you know that large language models are very huge in terms of parameters. So I think that they store not only knowledge, they also store like the grammatical correctness of the generated sentence. But if you ask a human to find an answer, the human could refer to a book or a text and kind of change their answer, like, because we don't store so much knowledge. So is there any direction in that way that the language model can kind of refer to, kind of retrain itself when the user is asking the question rather than just using the retrained parameters?
That's a good question, and we've done some work on sort of pushing on this front. Maybe I'll see if I can bring up a slide while we're thinking about it. But the idea is to retrieve the relevant information. So training LLMs to be able to do a Google search, for example, and not just make up a number, but put the results of the Google search and then see what you can get. I think, yeah, people are definitely looking at that. That might be a better sort of way of how things will be in the future, for sure. But we sort of, when you push it to an extreme, the model tends to not do very well, even in those situations. Let me see if I don't have an example, but yeah, that is definitely something people look at. Actually, I did find an example. Does it come up? Okay, yeah. So this is a fun example, which is why I wanted to bring it up. We call this knowledge conflicts. And the idea is that there may be things that are just not true anymore. So what we tried to do was we would ask things like, we would give it a paragraph. We would say, like, here's the paragraph. The iron gates in the clouds are guarded by St. Peter. And then we ask the model, who do we meet at the gates of heaven? The model says St. Peter. That's expected. But then what we do is we give it a different paragraph where we change St. Peter and replace it with Bon Jovi. And then we say the iron gates and the clouds are guarded by Bon Jovi. Who do we meet at the gates of heaven? And we've given it the right piece of information here. And the model still says St. Peter, right? Because it's very difficult for it to sort of change like whatever it knows about the case. So even putting the right information doesn't always solve the problem. Models are getting better and better at it, but this was a problem as well. Yeah.
Just because it has not been retrained on Bon Jovi.
Yeah, that's right. Yeah.
What if it retrains on the fly?
Yeah, some people are sort of thinking about those things like that.
We'll take one more question.
So at the very beginning, you mentioned that kind of the history of natural language is kind of a task model that then had a reading model, and the reading model grew and grew, and the task model kind of shrunk. Are there attempts to kind of attach other models onto this reading model? Like, for example, Wolfram Alpha is very, very good at doing math. You'll give it a question. So is there an attempt to kind of say, okay, now the LLM knows that it's getting into hazy territory, maybe it should, talk to another model to see what input it would provide?
Yeah, that's a great question. I will say that the short answer is people are definitely looking into things like that, right? Like LLMs are reaching to a stage where maybe you don't want them to be doing math. Maybe it's better to focus on the language, and whether it's new knowledge or some operation, it's better to sort of delegate it to something else. So yeah, definitely people are thinking about it. The tricky thing there is always getting the model to do that rather than just give the answer, right? Like the model doesn't really understand that it's in a state that it shouldn't guess. Getting a model to know, okay, I shouldn't answer in this case is actually tricky. And so, yeah.
That makes sense. Thank you.
We can continue the discussion at the reception outdoors, and let's thank Samir. Great talk. Thank you.